Hello folks, today in this video we're going to talk about magnetism. We're going to take a look at different types of magnetism and where it comes from, as well as the way that magnetic fields and forces interact with particles. Let's get started. So you might have heard of different types of magnetism and where it comes from. I think the very basic one that we've all heard of is ferromagnetism. Ferromagnetism is a strong attraction between objects resulting from permanent magnets. So these are the kind of magnets you played with in kindergarten science, where you've got the bright red North Pole and a oppositely colored South Pole, or if you played with kitchen magnets or those really strong little teeny magnets before, that's where ferromagnetism comes into play in our everyday experience. But we want to talk a little bit deeper about why does something have ferromagnetism, and where do those things come from? It comes from a little bit from a chemistry concept that you've probably interacted with before. That chemistry concept being that of paramagnetism and diamagnetism. If you remember, paramagnetism is a weak attraction to a magnetic field, and diamagnetism is a weak repulsion by a magnetic field. Well, why do they do that? You might remember taking a look at the electron configuration of elements. For example, boron's electron configuration is 1s2, 2s2, 2p1. If you were to take a look specifically at how those electrons fill in the orbitals, you have two electrons paired in the 1s, two in the 2s, and in the 2p, there's only one electron, and so it has a spin up, but there's no down in that orbital. And so you might remember that paramagnetism comes from unpaired electrons. Any element that has unpaired electrons is going to tend to be paramagnetic, whereas an electron or an element that has all paired electrons is going to be diamagnetic. Now, if you're looking at this periodic table, there are some more complicated things going on, but that's the general principle about where paramagnetism and diamagnetism comes from. So the source then of where magnetism is coming from is electron spin. Now, electron spin is a loaded term. It is useful to think about it like an electron spinning on its axis, but electrons, remember, aren't little teeny tiny spheres. They're much more complicated than that. They have a dual nature of wave and particle. So electron spin isn't literally electron spinning. The fancy term for it is intrinsic angular momentum, but it's a useful way of thinking about it. And if you think about spin, an object can obviously spin in one of two directions, either clockwise or counterclockwise, or we call it spin up and spin down in the case of subatomic particles. So the deepest source of magnetism is electron spin. But the way that those spins interact produces lots of different strengths of magnetism. Kind of returning back, diamagnetism is when all of them are, the electrons are paired. So there's a spin up and a spin down. You get paramagnetism when you have some that are unpaired, that are spinning upward or downward. But even paramagnetism is a weak attraction to our magnetic field. How do you actually get like a permanent bar magnet that you would stick to your fridge? Well, that gets into more complicated ideas of how the individual spins of all the atoms are oriented. If you have a material, sometimes each of the individual atoms might line up so that their spins are opposite. That would produce a material that even if each atom is paramagnetic, overall they would cancel out, and so it wouldn't be magnetic. That's actually most normal materials, but some materials like iron and cobalt and nickel in particular are able to take all of those individual atoms and line them up so that their individual electron spins are in the same direction. That produces a material that is ferromagnetic. And so that's where we get that strong permanent magnet from. But even then, you might have seen iron that is not magnetic. A paper clip on your desk, for example, probably isn't magnetic. Why is that? Well, in a material, you need to have all of the different domains of atoms lined up in the correct direction. So that's what this here is showing, where you might have a bunch of domains of atoms lined in the correct direction, but maybe there's another domain right next to it in a different direction. And so only when you get all of this to happen, where the electrons are unpaired, where each of the atoms is lined up with its neighbor in the correct direction, and then each neighborhood of atoms, the domains, are lined up do you end up getting a permanent magnet? So that's where magnetism comes from in one perspective. But another type of magnetism that you might not think about often is electromagnetism. But this is actually a really common form of magnetism as well. Electromagnetism is when a current flowing through a conductor also produces a magnetic field. This effect is called electromagnetism. If you take any wire and hook it up to a battery and let electrons flow through it, it will produce a magnet. And the way to think about that, like how to reconcile this, is that think about that spin analogy for electrons. Again, like I said, they're not actually spinning. But if you think about it that way, a spinning electron is a charge that is moving. And so moving charges in a wire is doing a very similar thing. And so that also produces a magnetic field. So we're going to use both of those kinds of magnetism in our study of how magnetism functions. So I first want to talk about if you have a magnet, whether it's an electromagnet or a permanent magnet, how it produces a magnetic field around it. Magnetic fields are very, very similar to our study of electrical fields. Electrical, they obey all the same rules. Electric field lines could not cross, therefore magnetic field lines could not cross. In electric field lines, they started from a positive and go to negative. Here, they start from a north pole and they go to the south pole of the magnet. So you can kind of think about north, positive, south, negative, same kind of thing with that there. What does a magnetic field line represent? A magnetic field line represents what direction a compass would point. Now, what do I mean by a compass? A compass is just another magnet, a magnet that can spin, and it shows us the direction. So if you actually take a magnet and you were to put a compass around it, it would always point along these magnetic field lines. So if you have this magnet here and you were to put a compass right here, that compass would point along the direction of that field line. The reason being is that the south pole of this compass will be attracted to the north pole of the magnet, and then the north pole of the compass will point away from that because it is repelled by the north pole of the magnet. So a compass is just a magnet, and it is able to show you the direction that a magnetic field line would point. This does bring up an important question, though, which is, on Earth, what direction does a compass point? Well, like we said, they always point along the direction of the magnetic field lines. So a compass always points towards a south pole, which you might be like, wait a second, I know geography. I know that if the Earth is here, the top of the Earth is the North Pole and the bottom is the South Pole. That's because we've named them incorrectly. The top of the Earth is a south pole of a magnet. We call it north because that's the direction that the compass points. It's the north part of the compass points that way, but it's pointing toward the south pole of the Earth's magnetic field. And then the bottom of the Earth is the North Pole, North Magnetic Pole, because that's the direction the compass points away from. So another fun fact to know there. The last interesting thing about magnetism that makes it different than electrical forces and electrical charges is that there are no monopoles. What do we mean by a monopole? If you take a magnet and you cut it in two, guess what you get? Two magnets. You don't get a North Pole and a South Pole. You get two magnets, both having a North and a South pole on them. In fact, you cannot produce just a North Pole or just a South Pole. And that's something very different about magnetism. Electrical charges, you can have a positive charge and a negative charge by themselves. You don't have to have a positive next to a negative every single time. But for some reason, magnetism seems to work differently, and you cannot separate a north and a south pole. So that's a bit about magnetic field lines and how they work. I next want to talk about how magnetism interacts with matter, specifically moving charges. So if you have a magnetic field somewhere, if you have a magnet and you have a charge, an electron or a proton or something next to it, that magnet will produce a force on that charge. We call it the magnetic force. So our equation for magnetic force is that the force of a magnet, and we use the letter B to indicate magnetism, not M, unfortunately. So E means electric, B means magnetic. So the force from a magnet is equal to QVB sine theta. So what does this mean? So F, of course, here is force measured in newtons. Q, we've seen before, that means charge in coulombs. And V here is the speed of your particle. So if you're having some charge, I'll kind of go down here and here's my proton. It's the speed of this proton going through that magnetic field that matters for this force here. The faster it's moving, actually, the more force there will be on that particle. Then the capital B is the magnetic field strength, how strong that magnetic field is. The stronger your magnet, the higher your B value, and it's measured in a unit called Teslas, not named after Elon Musk's terrible company, but instead named after Nikola Tesla, a very famous scientist that you might have heard of before. So a Tesla is our unit of magnetic field strength, and it is measured in newtons per amp meter. But just know that a Tesla is magnetic field strength, and you'll be just fine. It also depends on the angle that you're moving at. So if you were moving with the magnetic field, if this proton here was moving directly with the magnetic field, the angle between them would be 0. Sine of 0 is 0, so there would be no force on the particle. So a 0-degree angle produces no force on the particle, whereas a 90-degree or a right angle produces the maximum amount of force. In most cases, we're going to be taking a look at just right angle forces because that's much easier to take a look at. The next thing to talk about is what are these X's here and why are they appearing on this screen? The direction of the magnetic field could be in any direction, and we often need to think about this in three-dimensional space because we unfortunately live in a three-dimensional world. But this screen and the papers that we do all our math on are two-dimensional. So we need a way to represent that. This proton is moving to the left. This magnetic field is not moving to the left or up or down or to the right. It's actually going into the page. So this X indicates into the page / screen. So that's our way of indicating, hey, this magnetic field is at a right angle to the speed, but it's into the page that you can see there, rather than being like up or down. It's in. And then there's also a way to indicate going out. Going out is you would see a dot with a circle around it, and that means out of the page / screen. So that would show that it was coming toward you rather than away from you. One of the best analogies I've heard is think about it like in the direction of an arrow. An arrow has a point on it, and it has like a fletching on the back with the feathers, right? So the point means the arrow is coming out towards you. The X means the arrow is going, you're seeing it behind it going into the page there. So I now want to find out what direction this force is going to be. The direction is given by the most famous rule in physics, the right-hand rule. So I've given you a picture here of the right-hand rule, and you want to be taking a look at your right hand. Seeing my picture here, I'm going to go ahead and use this hand because I think this looks like my right hand to you. That's always tricky when you're teaching this to kind of like opposite those directions there. So hopefully this makes sense. Always use your right hand, never use your left hand. So the way the right hand rule works is you go in order from that force equation, starting with your thumb. It goes, we're going to ignore the Q. V is your thumb, B is your magnetic field, and then F then is your force. So V, B, F. And what it's showing you is if you line up with that V, my V is pointing to the left, and then my B is pointing into the page, right? That means that my force is going to be downward. So V is to the left, B is into the page, into the screen. That means my force is down toward the bottom of the screen there. So you can kind of draw it in as if this proton, so that would be the force of the magnetic field on that proton. So directions given by the right-hand rule, this always assumes the particle is positive. If it's not a positively charged particle, then unfortunately, it's the exact opposite you get. If you're doing an electron rather than a proton, you would just change and flip that answer so that it was the opposite way. So an electron here would be going, the force would be up rather than downward. Okay, let's take a look at some examples here. Moving my face out of the way here. I've got a bunch of different charges. And I want to think about what direction will magnetic force on each charge point. So try your right-hand rule, get it out, see if you can figure out which direction each of these charges will be pointed, and then take a look here for the answers. So for A, I would say that force is moving. Remember, it's V for the motion. So that one's moving to my right. And then the field, that's a dot. So it's moving out toward me. So right out toward me, that would be then that the force is down. So I get the force on this one to be down. And then for B, I get that still moving to the right, but now my magnetic field, because of the X's, is pointing into the page, and that means that I am going upward. So my force would be upward. Take a look and notice, by the way, a pattern here. It's always 3 different directions that are at right angles to each other. So you'll notice that if the particle is moving to the right, that means that left and right is already being used. The answer cannot be left or right. And then the field is going out of the page, so it couldn't be out or in. That means your only choices are up or down, actually. It always has to be everything at right angles to one another. Then you got the negative charge here for our C. This is exactly like B, actually, but now with a negative charge. And so you could use your right hand and say, okay, that's moving to the right, and then into the page. That would tell me upward, but because it's negative, I have to flip it and move it downward. And then hopefully you can see D is the exact opposite of A, and so that one would be moving upward. Hopefully that gives you an idea of how to use the right-hand rule. We'll, of course, look at some examples in class as well. Now, taking a look at how to use the equation, magnetic force on a moving charge, in terms of math here. It says here a proton is moving to the right. So here's my proton moving to the right with a speed of 2.0 times 10 to the 5th meters per second into a magnetic field of 3.5 Teslas directed inward at a right angle. So inward, nope, that's out. Sorry. Inward is the X's. So here's my magnetic field, and it is pointing inward, and it has a strength of 3.5 Teslas. It wants to know the magnitude and direction of the magnetic force on the proton here. So magnetic force, F sub B, is equal to QVB sine of the angle theta. I would use here the charge of my proton here, the charge of a proton being not 6, 1.6 times 10 to the minus 19th coulombs. The V is the speed of my charge, 2.0 times 10 to the 5th meters per second. And lastly, B is my field strength, 3.5 Teslas. I could include my sine here, sine of the angle, but because this is at a right angle, which is typical, this is going to be at 90 degrees. So what would be my magnitude? Do that in your calculator. When I did that, I got a field or a force of 1.12 times 10 to the minus 13th newtons, or rounding for sig figs, 1.1. Now it wants to know the direction as well, so I got to use my right hand rule for that. If it's moving to the right and then the field is inward, that looks like it would be an upward direction, upward force. Okay, one last thing for today, which is to take a look at the magnetic force on a current carrying wire. So we've been previously talking just about forces on charges, individual charges. But as you can imagine, if you have a wire carrying a bunch of charges, you could put a force on each of one of those, and it would put a force on the entire wire. So a current is just a series of moving charges. So a wire carrying a current will also experience a magnetic force. This is awesome because it's almost the exact same idea we just learned, just some different symbols. So the force on a wire is ILB sine theta, where instead of it being Q like it was for a charge, it's now I, which is the current going through that wire. Instead of thinking about the speed, we're now thinking about the length of the wire in meters, and then B is still your magnetic field. So it used to be QVB sine theta. That's the one for just a particle. And for a wire, it's ILB sine theta. The direction is exactly the same thing we did with the right hand rule, where you would use your thumb for the speed, which is the current going through the wire. The magnetic field would be the index finger, and then your middle finger would be the force that is on that wire there. But other than that, it works just the same for wires. Okay, folks, that was a lot about magnetism and forces. Hopefully that all made sense. Let me know if you have any questions. Other than that, have a fantastic rest of your day.